and welcome to our last week before finals. This is crazy that we are here at the end. So, here's what we have going this week. We have 2 days of time to work before we get into our final exam. And so, on this first day, we are going to wrap up some introductions into working with polar equations, and we are going to work with polar graphing. Now, you might be picking up, we're not going to do an end of chapter assessment, but this is really this is a unit that I believe is completely worth doing still just on its own because it has so much cool stuff, so much new things different. And this section specifically, if you think I am out, I am not going to be tested on this, I'm done, stick with me here because I promise I have picked some cool stuff to end with. And I remember learning this, it blew my mind. So we are going to get into polar graphing, and then the second day of this week we will be doing review. So let's go ahead and get started. So what we're going to do is we are going to look at how do I actually graph a polar equation on the polar axes, and then we're going to graph some by hand, and then we're just going to use graphing features to look at a bunch of cool graphs. So you should get excited. So here's what we got. The table that I'm going to give you for the next couple of functions was completed in radian mode. This is really important. If you try to calculate these in degrees, it's not going to work the way we want. So we are going to plot these points in order and connect them to make some interesting graphs. As we explore each graph, we'll name its shape, describe the symmetry, and identify the maximum R value that this graph reaches. For symmetry, we've got three options. The line theta equals 0, which is essentially the horizontal x-axis. The line theta equals pi over 2, which is the vertical y-axis. And then 180-degree rotational symmetry around the pole. And the pole is the origin. That is the central 0, 0 dot. So let's go ahead and get started. First disclaimer, this is why I think these are so fun. Up to this point, probably the most exciting thing we've seen is a hyperbola, which is just essentially, that's a bad sketch. There we go, which is essentially two parabolas. And maybe we've seen some wonky rational functions, but we are going to see some really cool things that you cannot graph with regular functions, but polar functions allows us to do a lot more. So here we go. Here is our first graph. We're going to plot these points in order. Remember, if the radius is negative, we're going to go to that value and then go the opposite direction. So 0, positive 2 would be here. So negative 2 puts us right over here. Remember that this line is pi over 6, pi over 4, pi over 3. So for pi over 6, negative 1.7, that would be right before 2. We follow that line to the other side. We should be at the second line, and I'll say 1.7 is about right here. Negative 1.4 for pi over 4, negative 1.4. So hopefully we're starting to figure out the pattern here. I'm going to go to the next line because pi over 4 is this middle line, and then if I go negative, that's over here. Pi over 3 is negative 1, so next line, and we're starting to see this curve that's following here. Okay, next up, when I'm at pi over 2, which is right up here at this line, I'm at 0. So what is happening is we are going line by line. So we did this one, this one, this one, and this one, except some of the lines had a negative radius, which is what put us the other side. So now keep continuing around these lines. We're going to be at 2 pi over 3, which is that second line after pi over 2. At pi, we are at positive 1. So let's go ahead and put a dot right there. Next up, 3 pi over 4, which is the middle line, we are at 1.4, which is kind of right between the halfway point. And then at 5 pi over 6, which is the next line, we are at 1.7, which is going to put us right about here. And then at pi over 2, or sorry, at pi, we are at positive 2. Well, let's see here. I'm going to pick a slightly lighter blue. It's the same dot. We've already done that one. Okay, let's keep going. If I did 7 pi over 6, that is 1.7. I already have a dot there. Same with 1.4. I already have a dot on 4 pi over 3. I already have a dot on 1, and then I already have a dot on, if I go to 3 pi over 2, 0, that overlaps with the dot at the origin. So essentially, we have started this graph and we have figured this out. Any more points that we do from here are just going to flip and they are going to overlap. So we can go ahead and connect this as best as we can, going around these points. And it will look a little bit rough in our sketch, but what did we just form? We just formed a circle. And so this one does not have a super fancy name. This graph is the graph of a polar circle. So this is our circle here, which is awesome to see. And this circle, in terms of its symmetry, if I could fold it across that x-axis line, that's the theta equals 0 line. And the maximum R value that it reached is the furthest circle out here at 2. So its max R value was 2. So nice thing to notice here is that when I had R equals -2 cosine of theta, that gave me the graph of a circle. So we'll see as we get into these more some trends with the equations and the graphs they produce. Let's look at another type of graph. This next one is 1 minus 2 cosine theta. Again, we're going to follow this same pattern. And if you just quickly glance through, you'll probably see some similar types of numbers because certain trig functions at pi over 6, it's going to give us the same number, but sometimes that number is positive, sometimes that number is negative. The same with all of the different values that end with the same denominator. So that's why we start to pick up some common answers as we add and subtract similar values. So let's go ahead and get started. All right, 0, we are at -1, so that puts us to the left right here. At pi over 6, that puts us at -0.7, so that's going to be somewhere around here. At pi over 4, we are at -0.4, so that is, if I pass through the middle, that puts me right a little bit less than halfway, but before the first radius. Awesome. And then pi over 3, it's at 0. So I'm going to put a dot on the origin, on the pole. Pi over 2, we are at 1. All right, awesome. Next up, at 2 pi over 3, we are at 2. So that puts us right about here. At 3 pi over 4, we are at 2.4. So that would be somewhere right around here. And then 5 pi over 6, the next line, we are at 2.7, which would be approximating somewhere around there. So interesting, looks like it's starting to form a spiral. All right, let's see if the spiral keeps going. At pi, we are exactly at 3. So let's go ahead and put that dot. Now it looks like as we come down, this pattern starts to mirror, going up to the second row, 7 pi over 6. That's this next second line over. We skip that first line. That's a pi over 12 line, which isn't a value traditionally given on the unit circle. But in order to have even marks, that's why we need this line. So that's why we skip it. Okay, so we're at 2.7. All right, the next line, we are at 2.4. You can start to go a little quicker once you pick up the pattern. 4 pi over 3, we are at 2. And at 3 pi over 2, we are at 1. Okay, cool. All right, next up at 5 pi over 3, we are at 0 again. Great. At 7 pi over 4, we are at -0.4. Okay, so where's 7 pi over, 7 pi over 4 is this middle line right here. So if we are at -0.4 on the middle line, that would be right about here. And then if we are at -0.7, that puts us right about here. Okay, so maybe you can start to see this. What you want to do is sort of trace, and we want to trace this like a connect the dots in a smooth line. So here's what we did. Our first point was the point -1. So that was here. We went like this through. We would follow this dot next in order through, around like this. I kind of missed a couple, but close enough. Through the middle and something like this. And this is a sketch of our graph when we connect it, which has this cool feature where it's got this kind of extra loop in the middle. This is like a circle with a dimple and a loop. And I hope you were thinking a little bit to yourself, wow, this is pretty cool. I've never seen anything like this before. I loved learning about these for the first time. So this graph is a special type that do come up often enough that we have given them a name. And this is called a limacon. So it is called a limacon, and this is a pretty common type of graph that we'll have. It's a It's a special subcategory. It's got a loop in the middle. And this does have symmetry. It is symmetrical around theta is equal to 0. And then it looks like the maximum R value that it reaches is that outside circle, and that is 3. Okay, for this next one, hopefully you're starting to pick up on how these are graphed. And so I'm going to move a little bit faster here just for the sake of the explanation. All right. Our next graph is an interesting one. It's R equals theta. So each time I'm on the different lines, when I'm on pi over 3, pi over 4, sorry, I switched those, pi over 6, pi over 4, pi over 3, pi over 2, all those values as we go, we're going to use the decimal approximation for that value as the actual radius. So as our angles get bigger, we should expect our radius to get bigger too. So first one, when theta is 0, hopefully that makes sense that R is going to be 0. So that's our first dot. Next up, pi over 6. The decimal approximation of pi over 6 is going to be 0.5. So these circles, we will go to pi over 6. We'll put 0.5 on there. All right, pi over 4 is 0.8. And then pi over 3 is about 1. Pi over 2 is about 1.2. Then, sorry, pi over 2 is about 1.6. 2 pi over 3 is about 2.1. So that would put us right above the second circle. 3 pi over 4 is about 2.4. And then 5 pi over 6 is about 2.6. And then pi is about 3.1. So we're going to keep going. All right, hopefully you can do these. So keep plotting these. I'm going to keep going. 3.9, 4.2, 4.7. All right, 5 pi over 3. We actually don't think I've ever graphed anything in this quadrant. 5 pi over 3 is going to be 5.2. And then 5.5, 5.8, 6.3. Oh, what are we doing here? Looks like it is forming some sort of spiral. And this is our graph here. This is a spiral that is formed by these, and it obviously I didn't approximate going through those points that great, but we are sketching this by hand, so we're doing the best that we can. So this graph is called what it looks. It is called the spiral, or it's called a spiral, but it is also sometimes called the spiral. I did not spell that right. Hold on. It is sometimes called the spiral of Archimedes, because he was the person to discover this, and it's done some cool things with it moving forward. So in terms of its symmetry, I can't rotate it 180 degrees and it perfectly land on itself. I can't fold it across the X or Y axis. So it doesn't have any symmetry. And because it keeps going, because we could keep increasing theta forever, it's not going to have a maximum R value. So we would say that max R value is none. So this is another cool graph. So far we have seen a circle, we have seen a limacon, we've seen a spiral. Now we're going to do a couple more, and we are going to use the calculator, or we're going to use Desmos. For the sake of time here, because these do get a little bit lengthy to draw by hand, we're going to start going through a bunch of these, and I'm going to use Desmos. I will eventually show you how to use your graphing calculator, but let's start with some Desmos graphs. So here's the first thing. You might think, whoa, how did you get Desmos to look like this? Well, let's go explore our settings. Generally, yours is on the grid. You should see next to it what looks like a spider web. That's our polar grid, and that's all you have to do. And then you want to make sure that radians is in green highlighted at the bottom. Okay, so now we have a polar graph. Let's go ahead and open up our graphing features, and the first thing we want to do is R equals 2 minus 2 sine theta. So here's the important thing. You want to go to the alphabet to get R. So we're actually going to type that there. R, go back to the home page, equals 2 minus 2, and then we're going to go find sine. And then we can't use X, we do have to use theta. Theta is in the very right side, and here we go. we're going to take this all the way up to, it should automatically do this for us, but it will take it from 0 to 2 pi. That's what we did. And here is our graph. How lovely is this? So this forms like a little heart shape, and I'm going to shrink this here and then go ahead and sketch it in. So it looks like it passes through. Let's identify a couple of important points that it goes through. 1, 2, 3, 4. So it goes down. Its lowest point is 1, 2, 3, 4. Its widest points on the x-axis, it crosses through 2 and 2. And then we can sort of do our best to sketch from here. 1, 2, 3, 4. Okay. So it looks like it goes, that's a bad sketch. Let's do this. Something like this. And this is a rough sketch of our graph, not quite as round as the one that we have on here, but with all of these, it's okay if you just are doing your best. And this, just like the heart name for a heart doctor is a cardiologist, this is called a cardioid. So this specific cardioid, I could fold it across the y-axis. So it is going to have symmetry over theta equals pi over 2. And it looks like the maximum R value that it reaches is 4. All right, so this is our first one, the cardioid. Now let's go ahead and look. The cardioid sort of feels like the limacon that we saw. And the equations look pretty similar with the numbers minus, but it looks like we get something a little bit different here. So we'll start to notice some patterns. Okay, so there's another one. Let's look at another one. So we need to pull up from the bottom to get the graphing feature. And then we're going to do R equals 4 cosine of 2 theta. And if you don't want to delete it all, that's also fine as well. So you have the R equals 4 cosine, this one's about to be one of my favorites, of 2 theta. Whew. Look at that beauty. We just graphed a flower. If this doesn't kind of blow your mind, man, I didn't do a good job this year because this is incredible. That is so cool. So while I am nerding out, let's go ahead and sketch it. I'm going to put it in this nice pink color because it feels very floral. Those flower leaves go up to a maximum radius of 4 on each of the 0.0 pi over 2. So I'm going to make a dot there for the accuracy of my sketch. 1, 2, 3, 4. And then down here at 4 as well. So then as best as you can, we'll make 4 loops. I'll do this one more. Oh, that one got a little wonky. Okay, here we have it. And this is daptly called, oh, I put that top one up one more. That should be right about here. I'm worried if I delete it, other things are going to go. Oh, not too bad. Okay, there we go. And this is appropriately called the rose. So this is a polar graph of a rose, and it actually has a lot of symmetry. So it's symmetrical over theta equals 0. It's also symmetrical over theta equals pi over 2. But yet we have yet to see that 180-degree rotational symmetry around the pole, and this has it. I could rotate it 180 degrees, and it would land on top of itself. And so this has 180-degree symmetry around the pole. I don't want to write that out. I don't think you do either. So we'll just say pole for that point. And its maximum R value is 4. Okay. What we're doing with these is, I know you might think there's a lot that we're going through. I'm showing you the main categories of polar graphs that we'll come across. We have a couple more that we're going to see before we explore into some more graphs. So if you at one point want to move on and just keep trying these out on your own, that is awesome as well. So here's what we have. So we have R equals R squared is equal to 4 cosine of 2 theta. So for this one, because there's an R squared, Desmos is awesome and it allows us to type it with the square. The graphing features on the calculator don't. And in order to do that, what we would do is we would square root if we want to graph it on the calculator, and then we would just type in, this gives us R equals plus or minus the square root of 4 cosine 2 theta, and you could just leave it like that for now, and then we would just graph the positive side and the negative side to get the whole thing. But I believe Desmos allows us to do this. So all we need to do is add a square onto the r. So let's do that, and it didn't like that. Okay, so then let's go ahead and do what we were going to do. So we are going to graph r equals, let me get rid of this, the positive square root. All right, we're just going to have to retype it. That's fine. Square root of 4 cosine of 2 theta. And all right, it actually did it for us, and it graphed the whole thing, which is incredible. Sometimes it only gives us half the graph, but we got the whole thing. If you only got half the graph, we could also graph r equals negative square root of 4 cosine of 2 theta, and it will add the other half. But looks like we got it all. We're good to go. Okay, so here is our graph, and this is super cool. It's like an infinity sign, and this is called a lemniscate, which I will show you how to write. It's a funny word, but it is a cool graph here. So this one, again, it has a maximum radius of 2. So we go out to the second circle, and then we form this little infinity loop. So it looks like it crosses through. Do our best to sort of approximate something like this. All right, so this is our graph of the lemniscate, and here is how you pronounce this. This is Lemniscate, lemniscate. And this has a lot of rotational or a lot of symmetry as well. It is symmetrical around theta equals 0. It's also symmetrical around theta equals pi over 2. It is symmetrical on that y-axis, and I could rotate this 180 degrees, so this is also symmetrical around the pole, and its maximum r value is 2. Okay, here's another fun one. So here we go. The next one, so what we saw is with the rows, it was r equals 4 cosine of 2 theta. We're actually about to see another rows, but it will look a little bit different. This one is r equals 3 sine of 3 theta. So let's see how the 3 theta changes things. So this is r equals 3 sine of 3 theta. Woo-hoo-hoo, look at that. That is pretty cool. Okay, r equals 3 sine of 3 theta. I got a rose that has 3 petals. So with the 3 petal rose, when we want to go to graph it, let's go ahead and identify the points that would help us plot this. So it looks like each of those petals goes out to the third circle. So that would be on this one all the way out to the very edge. And then it is on the pi over 6 line, so the second to closest ones to the axis. And then on 3 pi over 2. So here we go. And then let's go ahead and sketch our rose petals as best as we can. All right, we'll go through here. And we'll go through there. Awesome. Okay, so this is the rose, and this does have symmetry. I can't rotate it 180 degrees. It's not quite going to work for us, but it is symmetrical on the y-axis. So this is theta equals pi over 2, and its maximum r value is 3. Okay, we have 2 more of completely new graphs that I'm going to show you before we get into a couple of other cool graphs that we're going to look at. And these are a little less exciting, but it's interesting for me to see the parallels and how something we're actually used to seeing from graphing before shows up in polar form. So this is r equals 2 secant theta. So the graph is not quite as exciting, but it's interesting to watch these connections. R equals 2 secant of theta. And look at that. Huh, interesting. A perfect vertical line that passes through what we would call x equals 2, it hits the second circle and it goes from there. So that's actually super interesting. So this is a line. It goes through the second circle, and then we can just draw it straight vertical. I didn't quite get that, so I'll move it over. It goes just like this. So this is a line. It's symmetrical around theta equals 0. And in terms of the maximum R value, it's going to pass through all the circles infinitely, all those larger circles, so it's not going to have a max R value. So it's interesting that in order to graph a line, we don't use sine, cosine, or tangent, but we can use secant, and we can get a vertical line. Okay, here's the last new graph. Hopefully this should ring a bell when we did some of those polar conversions from equations, but this is theta equals pi over 3. Now here's the idea for this one. We can try to see, I actually haven't graphed this one in a while, and I'm not sure if Desmos likes this, but let's at least try it. Desmos takes most things. Let's try theta is equal to pi over 3. And here's the thing, Desmos doesn't like that. And this is pretty common of graphing features. I told you this before. This is the one thing we won't be able to graph. So let's go ahead and use our common knowledge here. What line represents, actually this was even negative pi over 3. What line represents negative pi over 3? We can even do this with the highlighter. So that's going to be, the negatives are going to be that line away. So negative pi over 3 is this guy right here. And then if I connect it all the way through, that would be this. And that is exactly how this works. For a line through negative pi over 3, we are just going to take that specific angle line, and it's a diagonal line. This is how we graph something that is not a straight vertical line. We use the angle measure, the theta, that we want that line to be on. So this is theta equals negative pi over 3. So this is a line. And I can rotate this 180 degrees, so this is symmetrical around the pole. And then it is not going to have any maximum R value. Alrighty, here's what we're going to do. We're not necessarily going to graph the rest of these, but I have given you a couple of other graphs that I think are really cool in here that are a little more basic graphs. So let's look at a couple more and see what happens. We'll play around. We might not even graph them all. If you want to go around and name the curve, you can do that, and I can tell you some of what these are going to be called. So let's go ahead and open Desmos back up. And actually, I'll show you later how to use the graphing calculator. So let's go ahead and open up Desmos. And so we are going to do R is equal to 5 times the sine of 2 theta. And here we go. We got another rose, but it is a 4-petaled rose, and it is, rather than hitting all the axes, it is halfway between them. And since we're on Desmos, let's go ahead and we can play around a little bit and see here. I would encourage you to do this. What if I changed the 2 to a 4? Whew, look at that. We now got an 8-petaled flower. What happens if I change it to 6? Whew, my goodness. We got I would assume, yep, we got a 12-petal flower. What if I did an odd number? What if I change it to 5? Interesting. Whew, I always like this one. So if you change it to 5, you actually get exactly the number of petals. So if it's an odd number, we have 5 petals. If it's an even number, we have double. Let's try, there's 7, which is pretty cool. What is a 20 petal? This is 10. So this is really fun to play around with, which we'll get into. So those are some of the ways to play with the florals. Let's go ahead. I think this next one, r squared equals 16 2 theta, is a very cool one. So again, whenever it's r squared, we can't type that, but we can use the square root. So we'll do r is equal to the square root of 16 sine of 2 theta. And here is this one. And then let's see if I add in the negative, does that do anything? R equals negative square root of 16 sine 2 theta, and it's the same graph. So this one is a sideways lemniscate. So it's also a lemniscate, so it's not a new phrase, but it is tilted. All right, so that's another cool one. And let's see what the last couple we have are. I really like this next one a lot. R equals negative 1/2 theta. So R equals negative 1/2 times theta. I love this graph. It's so cool. It's an infinite spiral. You can keep zooming out. And if you want the spiral to keep going, so this went to 12 pi. So this showed the spiral through 12 full circles of angles. Let's see what happens if I go to 2 pi. It just gives me like a shell. It gives me a partial. If I take this to 4 pi, I get more pieces. So with polar, you can control what section of the graph you have based on what angles you want. So if I want to go from 2 pi to 4 pi, I can cut off part of these pieces. Okay, I think I just put one more on here for you. I am having so much fun. Maybe it's infectious. Maybe this is the entertainment you need. Miss Tilly looking at polar graphs for your time at home. So here's what we got. Last one. R is equal to 2 plus 4 cosine of theta. Okay, here's our last one. This is I just blanked out on the name. This is a limacon, and it is going the other direction. So you can, if you want to try to figure out what makes these happen, play around with the different numbers. What happens if I make this a 4 plus, rather it was a 2 before. That makes it a cardioid, which is interesting. What happens if I make the first number bigger? It takes away the loop and it stretches it out further like this. So what if I made it a -2? It still makes a loop that goes through like this. So there's a lot of really neat things that are happening here with this graph as we compare and as we look at the different pieces. All right, I am finally done showing you all these cool and exciting graphs, but I have a lot more. Let me go ahead and unzoom. This is going to be worth your time. On the next worksheet, we are going to go through some really, really incredible graphs. They are awesome. And this is what we do is we actually use the graphs I've shown you today as a basis. And also some people just played around with crazy numbers to see what they can come up with. And this is going to be worth your time today. So if you want to practice more of these, go for it. There is a worksheet to practice it. But I give you my complete permission to not do the practice that comes with this and come watch the really cool graphs or to do them on your own. Okay. There's something that looks like a tornado. Huh, I don't know. Okay. All right, that is the end of these notes. So please from here, either you have two choices, but you have to do one of those choices. Go and watch the cool graphs, or you can choose to complete the practice and to work on graphing some of these on your own. All right, congratulations. You have finished new content for pre-calculus. If you made it this far, even in this video, props to you. Have an awesome rest of your day.